Humans often receive information in discrete steps. Think of when you read a book or watch a movie, where concepts, characters, or locations are unveiled one at a time. Each time we learn a new concept, it is added to an ever-growing mental representation of the world, a big map comprised of the different concepts that we know. We can view such a mental map as a knowledge network, with concepts represented as nodes and the relationships to each other represented as edges. In this work, we formalize curiosity as the process of building a growing knowledge network. To evaluate curiosity-driven information acquisition, we use Wikipedia browsing histories gathered from 149 individuals. Based on the page transition information in this dataset, we construct a growing knowledge network for each individual. Here's an example of a curious learner browsing Wikipedia and building a knowledge network in the process. Starting with the page for cats, depicted here as a node, let's examine how the learner's knowledge might grow as a consequence of visiting different pages. After learning about cats, our explorer next visits the Wikipedia page for night vision. This results in the addition of a new node to the knowledge network. Additionally, we add an edge between the two concepts, since the page for night vision connects to the page for cats through a hyperlink. Next, the reader visits the Wikipedia page for color vision, which hyperlinks both to cats and to night vision. As a result, we add the color vision node and two edges to the growing network. Revisiting the page for cats from color vision does not result in any changes to the network, as the concept of cats and its relationship to other known concepts remains unchanged. Finally, the browsing session terminates with a visit to the page for Egypt, adding yet another node and an edge to the network. Knowledge growth through curiosity is not only about acquiring new conceptual information, it is also about retreading and reconsidering what we already know. We propose that such reflection entails moving concepts flexibly in relation to one another. In the conformational change theory of curiosity, we formalize a drive for conceptual flexibility. To see how we can measure flexibility in networks, here's a simple example of a network that consists of 4 nodes and 4 edges. All edges in this network have the same length. Measuring flexibility requires that we embed an object of interest in physical space. So let's assume that the network resides in 2 dimensions, as if it were lying on a table. In the plane of the table, the network can move in several ways. Rigid body motions correspond to degrees of freedom where the entire network moves as a whole. For instance, the network can rotate, with the extent of rotation specified uniquely by an angle parameter. Or it might move horizontally and vertically. Collectively, rotation, horizontal translation, and vertical translation constitute 3 rigid body motions available to any object embedded in 2D space. Another set of movements, each associated with a conformational degree of freedom, corresponds to changes in a network shape. A conformational motion alters the Euclidean distance between unconnected pairs of nodes. In addition to the 3 rigid body degrees of freedom, this network also has a conformational degree of freedom, whereby it can undergo a deformation from looking like a square to looking like a diamond. While the number of rigid body degrees of freedom is determined solely by the embedding dimension, the number of conformational degrees of freedom also depends on the network structure. For instance, if we were to add a new edge along the diagonal, the network would lose its only available conformational motion. Given the embedding dimensionality and the number of nodes and edges in a knowledge network, we can measure its flexibility as the number of conformational degrees of freedom that it possesses. Here's an example using our curious Wikipedia reader from before. Beginning with the node for night vision this time, we assume that the network is initially embedded in one-dimensional space, depicted here with the horizontal white line. Visiting the page for color vision adds a node and an edge to the line. The network can move as a rigid body only along the line. It cannot be rotated or vertically translated. The shape of the network cannot change either, and therefore it has no conformational degrees of freedom. Next, if the reader were to visit a page, such as the one for hue, that connects only to one of the 2 present nodes, the number of available degrees of freedom would remain the same. The network can still be moved horizontally, but cannot be rotated, moved vertically, or deformed conformationally. Adding edges disproportionately to the number of added nodes takes away degrees of freedom from a network. For instance, if the reader were to visit a page that connects to both existing nodes, such as the page for cats, adding 2 new edges would lead to the loss of too many degrees of freedom, resulting in the network becoming overconstrained. A single dimension would no longer suffice to embed the growing network. In our framework, we assume that such an overconstrained knowledge network results in a form of cognitive dissonance, whereby competing constraints between concepts cannot be resolved. Whenever this occurs, in our model, We alleviate the tension by incrementing the network's embedding dimensionality by 1. The two-dimensional network can translate and rotate as a rigid body. However, it has no conformational degrees of freedom as its shape cannot be changed. Visiting the page for Egypt, however, would add a conformational degree of freedom. If instead of Egypt, which connects only to cats, the reader were to visit the page for frequency, which connects to all existing nodes, the network would become over-constrained in 2 dimensions, and need yet another increment in its embedding dimension. Considering the conformational change theory, we hypothesized that growing knowledge networks derived from Wikipedia would exhibit greater than chance capacity for conformational change. Scan the QR code to find out more about knowledge network flexibility and a broader network space perspective on curiosity.